Section 5.6, inverse trigonometric functions. We're going to try to differentiate these things. But before we try any sort of calculus with this, let's do a quick review of some inverse trig functions. So before we do the inverse trig, let's just do the forward trig. Recall that sine of pi over 3 is the y value on the unit circle that corresponds with the angle pi over 3. So therefore that's just root 3 over 2. Sine of 2 pi over 3, well, we'll go to this angle over here and we look at the y value and it's, oh look, it's 3 pi over, or root 3 over 2 again. That shouldn't be surprising. We've seen these functions before. When we look at cosine, we're looking at the x value. So again with pi over 3, this time we'll look at the x value. We get 1/2. And then if we look at negative pi over 3, okay, wait a second, that's going in the opposite direction. That's down here. So that, oh, wait a second. Okay, so we get the same answer again. All right, notice that this is a different change between pi over 3 and negative pi over 3 compared to up here because sines and cosines are not the same function. Anyway, now we look at tangent. That's going to be y divided by x. So that's going to be root 3 over 2 divided by 1/2, which is going to give us root 3. And as you might expect, I'm looking for another angle that gives me the same answer. That's going to be 4 pi over 3. Same x value, same y value, just flip both the signs. So the answer works out to be root 3 again. So as we can see, these functions are not one-to-one. They do not have an inverse function unless we restrict the domain, because we're getting the same output twice using different inputs. So we restrict the outputs to be between negative pi over 2 and positive pi over 2 for the arcsine function. So instead of saying, oh, it could be pi over 3 or it could be 2 pi over 3, we just pick this one for here. So the answer to this is pi over 3. That way everyone gets the same answer every single time. Likewise with cosine, inverse cosine, we don't go from negative pi over 2 to positive pi over 2. Instead we'd go 0 to pi. That makes sure we hit all the values. So that's going to be pi over 3. And likewise with the tangent function, we have to restrict that as well. That's going to work the same as the inverse sine, except we don't include the endpoints because of asymptotes. But the answer to that is going to be also pi over 3. We don't get two different answers for our inverse trig functions because then it wouldn't be a function. All right, so just a quick review on that. Now, if we are asked to evaluate these things like this and we don't have a calculator, then, well, let's take a look. We're taking the sine of the arctan of 5, but the arctan of 5 is an angle. I'll call it theta. And if theta equals the arctan of 5, then that means that the tangent of theta must equal 5. So I'll build a triangle, and I'll make theta be right here, and its tangent is 5. So I'll put a 5 here and a 1 here. Pythagorean Theorem tells us that this hypotenuse is square root of 26. So if I'm trying to take the sine of the arctan of 5, that's the same as taking the sine of theta. But I can take the sine of theta because I've got a triangle right here that tells me how to do it. We get 5 on the top and root 26 on the bottom, and we're done. Unless you feel like rationalizing. Same idea with this one. This is my theta value. This is arc cosecant. So if theta equals the arc cosecant of negative 13 over 12, then that must mean that the cosecant of theta equals negative 13 over 12. Now, if you don't like that equation, then just flip it. Sine of theta equals negative 12 over 13, and we'll put this down here. It's got to be quadrant 4 because of the domain restrictions. And we put the negative 12 here. We put the 13 here. This is a 5, 12, 13 right triangle, so I'll put my 5 up there on the x-axis. So now when I'm trying to find the cosine of theta, I just use the triangle and I see that it's 5 over 13. And I move on to the next problem. We've got a more algebraic thing here. We've got the secant of the arc cotangent of x minus 1. This is still theta though. We're still going to call theta equal to that argument. This is the arc cotangent of x minus 1. Which means that the cotangent of theta must equal x minus 1. So, again, build a triangle. We'll assume quadrant 1 just for ease. cotangent would put an x minus 1 here and a 1 right there. And then we use the Pythagorean theorem once again. And don't get too fancy with this. We've got to square the x minus 1, and we've got to square the 1. Now, if you feel like expanding that out, that's great. But you don't have to. You can just leave it like that. So now that we take the secant of this crazy angle, secant is the reciprocal of cosine, so we're going to take that hypotenuse and put that on the top. So the hypotenuse is the square root of the quantity x minus 1 squared plus 1 squared. And we'll divide that by the horizontal distance of x minus 1. And again, that's your final answer. And this is kind of nice because we're able to take something that starts out with trig values and turn it into something that is completely algebraic, which can be useful. So we'll just finish this up with one last example. Same idea. This is the angle right here is the argument. So we'll say that theta equals the arcsine of x minus h over r, which means that the sine of theta equals x minus h over r. When we build our triangle, our horizontal or vertical distance is x minus h, our hypotenuse is r, so our Pythagorean theorem tells us r squared minus x minus h squared inside the square root is that missing side. So when we take the cosine of theta, we get that crazy square root of r squared minus x minus h squared, and we divide that by